We title our work 3D-IDE 3D implicit depth emergent and introduce RGB-only 3D scene understanding through training time geometry. 3D-IDE uses depth, pose, and a 3D teacher only during training, so the visual encoder internalizes geometry and inference stays RGB only. Current 3D MLLMs create awkward inference costs because video-based MLMs for indoor 3D scene understanding mainly use two approaches. Explicit 3D injection requires per pixel depth or pose at test time and suffers double information loss from pooling and voxelization. Alternatively, dual encoders separate 3D and 2D models but yield high latency, larger memory, and misaligned features. Our core question: can a model acquire 3D awareness without either crutch? Explicit 3D injection suffers from two main losses. Pooling collapses patch points to a single token, while voxelization merges distinct 3D points. The pipeline first back projects the RGB frame and 2D patch to the point cloud, but coarse aggregation loses fine, grained 3D structure before encoding. Dual encoders create a late fusion burden because they require a large external 3D encoder and introduce a representation gap from misaligned. Frozen objectives. This pushes the fusion task onto the LM, increasing inference path complexity without using explicit pose or depth at test time. Our core idea, the implicit geometric emergence principle, IGP, treats 3D as privileged supervision available only at training. The encoder must organize features that a deliberately weak decoder can recover as geometry, and we discard that decoder after training. Thus, a single token stream carries both semantics and geometry without fusion modules or test time 3D input. The green box marks a privileged module that 3D-IDE uses only during training, so inference has no test time dependency. Two parallel gradient signals guide the encoder, a weak depth validator, and a frozen 3D teacher. At inference, 3D-IDE converts RGB video to unified tokens for the LM with zero added latency. Our method relies on three training. Only geometric signals the geometry loss, the cross-view consistency loss, and the global alignment loss. The geometry loss uses a weak depth decoder and applies uncertainty, weighted L1 in both value and gradient space. The cross-view consistency loss applies L1 between warped and predicted depths using pose. The global alignment loss aligns aggregated tokens with a 3D teacher. We remove all geometric modules at inference, only the encoder remains. A strong pre-trained depth decoder would relieve the encoder, but we use a low capacity from scratch validator instead. This design biases optimization toward organizing geometric features in the encoder's token space. The validator thus acts as a lightweight readout, and ablations show it is at least as effective as a strong pre-trained head. Our experimental setup uses a Seglipi encoder, Qwen27B language model, and Eleve, next framing with 32 frames per scene. The baseline uses video 3D LM after removing explicit 3D injection and uses only RGB at inference. We evaluate on task including scan-refer, multi-3D refer, scan-to-cap, scan-q, and probe geometry via an API. Our RGB-only model achieves state-of-the-art in generalist 3D scene understanding, performing on par with methods using explicit 3D at inference. Headline: we deliver the best RGB, only generalist results on grounding and match 3D input models on key tasks. Geometric probing tests a frozen encoder on dense correspondence and surface normal estimation, and all four metrics improve with IGEP. This indicates the visual tokens encode 3D structure. The language head does not learn it alone. Ablation results show every IGE term contributes, and all components together produce the best results. The weak from scratch validator matches or slightly outperforms pre-trained heads. This confirms the encoder internalizes geometry. Our approach incurs 12.9% fewer parameters and 55.3% lower inference latency versus dual encoder baselines. With no depth sensor, camera pose, or external 3D model, inference relies solely on RGB in our encoder. Qualitatively, for 3D visual grounding, ours blue matches the ground true 3D box, while the baseline RAID mislocalizes. Scan-refer referring expression localization shows our method's outputs align more accurately with annotated objects. For 3D dense captioning, our model correctly identifies objects and spatial relations and closely matches ground truth compared to the baseline. A higher CEDAR score measures our scan-to-cap captions as more descriptive and relational. On 3D visual question answering, our model answers based on spatial relationships, whereas the baseline selects salient but incorrect objects. This demonstrates our capacity to encode spatial understanding in ScanQA. To summarize, privileged supervision trains visual encoders with geometry and lets them infer from RGB while internalizing 3D structure. Geometry truly resides in the encoder, not in the validator. The validator only acts during training. Finally, we deliver the best RGB, only generalist results for grounding and QA, and achieve double the inference speed of dual encoder baselines. Thank you for your attention, and our code is online.